We ended the previous video by introducing Fisher information as the expected value of the second derivative of the log likelihood function. So if you haven't seen that video, please go back and just remind yourself what a score function is and what the Fisher information is. But we said intuitively large information meant I had a lot of information about what the value of the parameter I'm interested in is for my sample. And that was reflected in the fact that if I tried to change my belief about what the parameter value theta should be, I would have big changes in the likelihood function. So if I'm improving my estimate, I'd have a big change in the likelihood upwards. If I was weakening my estimate, coming out with the worst estimate, I'd see a big drop in the likelihood function, versus something where I had a small amount of information in the sample, where making large changes to my thought about the parameter value might not change the likelihood that much. Now, related to that, the Fisher information can give us a bound on the minimum variance which an estimator can have. Now, we're not going to prove this formally because it's beyond the scope of this subject, 37262 mathematical statistics, but the variance of an estimator cannot be less than the reciprocal, than 1 over the Fisher information. So the variance of my estimator theta hat has to be greater than or equal to 1 on I of theta, where I of theta is the Fisher information related to the log likelihood of my sample set of observations x for the parameter theta. Now that's known as the Cramér-Rao bound, named after these two gentlemen. One of them lived to be 102. So there you go. Statistics can keep you alive, seemingly. We can define the efficiency of an estimator by saying what proportion of the Cramér-Rao bound the variance is. So we define the efficiency of an estimator, the efficiency of theta hat, by being 1 over the Fisher information times the variance of that estimator. So the efficiency, therefore, because variance is non-negative, Fisher information is non-negative, it has to be between 0 and 1. You can sometimes see relative efficiencies that says how do the variance of these two estimators compare. So relative efficiency doesn't necessarily need to be between 0 and 1. It has to be non-negative, but that's just comparing the variance of one estimator to another. In general, when we talk about efficiency of an estimator, we tend to be compared to the best possible theoretical one, which is the Cramér-Rao bound. Let's take the simple example of a binomial variable with parameters n and p, where I know n, but I need to estimate p. So this might be like telling somebody to flip a coin n times, where I know n, but the coin has a chance p of landing heads on each flip. I just don't know what p is, and I ask the person to tell me how many times did the coin land heads. I can write down, if I asked k different people to do this, I can write down x1, x2 to xk, being how many heads each person returned. So the log likelihood is just the natural logarithm of the likelihood function, so is the sum of the natural logs of the probability masses of x1, x2 up to xk. Pause the video now if you just want to double check how I've tidied that up, but that's the slightly tidied up log likelihood function. So when I differentiate it with respect to the parameter p and set that derivative to 0, I can obtain the maximum likelihood estimate for the probability parameter, which is the sum of the xi's divided by kn. But how variable is that estimator? If I kept repeating this experiment of getting k people to flip n coins each and return the results, how variable would my estimate p hat be? Well, k is a constant, n is a constant, the xi's are definitely not constant. So if I have the variance of something times a constant, I get the variance of the something times the constant squared, so the kn in the denominator becomes k squared n squared. The variance of the sum of these xi's will just give me npk 1 minus p, because they're independent. Each has variance np 1 minus p, and I'm adding k of them. So when I start to tidy that up a little bit, what I will get is I will get p times 1 minus p divided by kn. So if I work out the Fisher information, which is the expected value of the second derivative of this log likelihood, I'm just differentiating, well, the statement that I set to 0 to find the maximum likelihood estimate again, well, the negative of that. So I differentiate this again and take its expectation. And tidying that up, I get the Fisher information being npk over p squared plus nk 1 minus p divided by 1 minus p all squared. So when I tidy that up a little bit, I get nk divided by p 1 minus p. So if I look at the variance of my estimator p hat, and I look at the Fisher information, you may notice that 1 is the same as the other, just upside down, that 1 is the reciprocal of the other. So in other words, the maximum likelihood estimate here has efficiency of 1. It reaches the Cramér-Rao bound. There isn't any estimator that I could come up with to estimate the value of p, which will have lower variance than the maximum likelihood estimate. And so in this case, it's unbiased as an estimator, and it has minimum variance. It is the best that we can do.